Hello guys, welcome back to Zone African Motives, still on industrial electronics and two. So we shall consider our revisions now from the question paper that we wrote in July, that is for the August exams. So quickly rushing through the questions that we have. So as you know, guys, the next paper, one that you write. So make sure that you read your instructions and information carefully, of which everything here is clear. So we are having the first question, that is question number 1, where we are given 1.1 to define the following terms that are used in electronic theory. So that is in electronic theory, how do we apply these terms? All right, how do we apply the terms that we are given? The first one, we are given the conventional current in this case. All right, so whenever I talk about the conventional current, that's the movement of current from the positive to negative. So this one is simply the movement of current. All right, so you're referring to the movement of current, in this case from positive, all right, from the positive to negative. All right, so that's how we can simply define this, the movement of current, meaning to say is the electron flow. We have got the electron flow and we've got the conventional flow. In this case, like if you've got a negative here and you've got a positive this side, all right, we are going to have this in this case. So this is a negative charge, a positive charge. So the electron flow is taken from negative to positive like this, while the conventional flow is one that is taken from positive to negative. So this is the difference between these two. So this is the one that we are referring to as the conventional current in this case, or the conventional flow of current. And here we are talking about the electron. This one is the electron flow in this case. All right, so these are the two differences that is we need to note about this. Is simply on the movement part. All right, so let's check the other part on 1.12, where we're given an element. In this case, what is an element? This one, I think it's a clear one, whereby we're referring to a substance that cannot be reduced or changed. So this one is simply is a substance. So you're gonna have this is a substance that cannot be reduced. So it cannot be reduced in terms of either size, or cannot be changed. It cannot be reduced or cannot be changed. That is what we are supposed to have in this case. Then we have 1.13, whereby we've got a trivalent. Tri, that is it means three. So a trivalent atom is simply an atom with 3 valence electrons. Tri, it's 3. Penta, it's 5. All right, so this one, that's simply an atom with the 3 valence electrons. All right, with the 3, or you can just write this in words. All right, with the 3 valence electrons, meaning to say we are referring to the electrons in the outer shell in this case. So for example, which examples that we can actually just apply for our trivalent atom? We are talking about such as the indium, right? So we've got the indium there. We've got something like gallium, which is, you're supposed to also know these ones. We also have boron there, and also aluminium. So there are actually a lot that we can list, but in this case, just few. All right, so this is just the list of what are the trivalent atoms that we have. All right, on 1.14, we are given to define another part, which is the impedance. Impedance is just like resistance in our normal DC circuit, but impedance, we refer to this in AC circuits. So remember, the resistance is the resistance to the flow of current. So it's the same thing that we are going to have, but this one is the total opposite flow of current when you're talking about a combination of resistances and their reactances. That is where by now we refer the impedance. So this one, we're gonna have this as the total. Let us just have this as the total opposition. So that's the total opposition to the flow of current. So referring to the flow of current in this case, which is the alternating current, because we're referring to the AC circuit. So that will be the alternating current. Okay, so this is the major part that you're supposed to be working with, but not just the alternating current that we are talking about. It must be also considered from the total resistance that is taken with reactances. All right, so we said the total opposition to the flow of alternating current in a circuit. All right, in a circuit, in this case, comprising of resistors and reactances. All right. So we must have resistors and the reactances. The reactances are the one that we are taking from, let's say, there is a capacitor. We have got XC, that's the reactance, whereby there is an inductor. We have got XL, which is the inductive reactance. That's what we are simply having in this case. Then we have got the rectification. So as long as we are working with these definitions, all you need is to understand the topic that has got that part. All right, so on our rectification, we understand the process of converting alternating voltage to unidirectional voltage. So this one from AC to DC. All right, so that is, let us just say, is the process. It's a process that's going to happen, but this process is of converting, the process of converting. We are going to convert an alternating voltage. So we are going to have the alternating voltage to a unidirectional voltage. That's a unidirectional. So voltage in this case. All right. So that is we start with AC, then we end up with a DC. All right, that is the concept of rectification. So that was just 5 marks for that, just to work with your definitions and so forth. 1.2, indicate whether the following statements are true or false. Choose the answer and write only true or false next to the question number. All right, let us start with the first part. Angular velocity is determined by the expression omega is equal to 2 pi ft. All right, this is actually false. Omega is equivalent to 2 pi f, not 2 pi ft. It's 2 pi f, all right, which is measured in rad per second. So this is false. So you see, they just tempt you with this t here. The t is not there. The t is found now when we are writing the final, like, voltage is equal to V max. Then we have got sine omega t, omega here t, whereby we are going to have 2 pi f t as sine there. So the omega here is the one that is for 2 pi f. T is not part of omega, it's part of the sine, not the part of this omega. No, so that was a false. All right, let us check the other one. In this case, 1.22. In biasing a PNP transistor, the base is negative, all right, with respect to the collector, and the emitter is more negative than the base. All right. In this statement, this is actually false again, because in the biasing of a PNP, what we know is that the collector is more negative than the base. The collector here, this part here, we'll be referring to the collector. The collector is the one that is more negative to the base in our statement. All right. So so the first statement is fine, but the second one now, it must be the collector there. All right, 1.23, we are given the photodiode is operated under both the forward and reverse biased condition. Is it true? A photodiode, this is also false, because a photo diode, remember, it is under a reverse bias. It operates under a reverse bias, this one. So that was a false. 1.24, we are now given that if two waves are in phase with one another, their frequency is the same. This is true. For the waves to be in phase, they must have the same frequency. To maintain in phase, they must have the same frequency, which is actually true. 1.25, we are given the maximum value is also referred as the peak-to-peak value. All right, this is false. The maximum value is just the maximum value. It can be referred to as the peak value, not a peak-to-peak value. A peak-to-peak value is the one that is taken from the maximum to the minimum, whereby this is the maximum value, this is the minimum value. So the peak-to-peak is the one that is taken from maximum to minimum, the difference between. So we can't say the peak-to-peak is our maximum value, no. So because we know that this peak-to-peak is given as 2 times maximum value, which is V max, or simply V max minus V minimum, maximum value minus minimum value. So it's false to say the maximum value is also referred to as the peak-to-peak. They're different. All right, so that is some of the smaller things. They'll be just testing you to see if you have the idea of that particular part that you're given. You have to work with the general knowledge of that particular topic to understand these typical questions, especially on choosing true or false. Question 2, there we are given to refer to the DC circuit below in Fig 1 and answer the following questions. All right, so this was our DC circuit. All right, this one is so big. All right, anyways, let's have it this way. So if you are to analyze our DC circuit, you can see here we've got our voltage source with the positive, the longer part here being our positive, negative, meaning to say the current is flowing this direction. We're having the total current of the circuit. So it is going to pass through R1. This current from the supply here is going to branch. After this, we've got a parallel combination. So we're going to have our current branching this side and this side. All right, these two currents, they are going to flow through their resistors, and after they here they are going to enter this combination. Remember, from your Kirchhoff's law, these currents will be at this point, then they come back now as the total current. So that is the current that is flowing here is still the same. It only changes when it is in the parallel circuit, when another one is transferred this side and another current is transferred this side. But by checking all these currents together, they are going to connect back from here. They are going to connect back, giving us the same total current that we had before. So that is the idea there. All right, so let us check what was our question. Calculate the total resistance. The first part of our question 2.1 was to calculate the total resistance, and that is 8 marks for that. All right, so let us see how we're supposed to have our total resistance here. Because of this diagram, which is too big, I'm just going to calculate it aside so that we see also as we analyze it from the diagram. All right, so that was 2.1. We need to calculate the total resistance. So if we are to check on this circuit, this branch here, on this branch, we can simply add these because they are in series. And in series, we know that we can simply add. So R3, R2 and R3, we can simply add these two because they are in series. So we are going to have the first series, which is R2 plus R3. All right, so these ones we're just going to add 25 plus 25, which is going to give us a 50 on your calculator. That will be a 50 ohm. All right, then we move on to this combination here. In this combination, if we check properly, we have a parallel, then a series. So we are going to have a parallel here and combine it with this resistor to make it a series. All right, so in parallel, we know that that is product over sum. So this one is going to be our first parallel combination. So we are going to have RP1 being the product over sum of what? R4 and R5. So we are going to have R4 times R5 over R4 plus R5. product over sum of the resistors. All right, so let us calculate this and see. So that means RP1 is going to be 17.8. So that's 17.8 times 6.8. So this was 6 comma, there's a comma there, comma there. So that's 17.8 by 6.8, everything over the sum. So you're going to add this to 17.8 plus 6.8. All right, so that gives us the first parallel combination of these two, which in this case, it was 4,920, something like that. If you convert to, if you change to the 3 decimal place concept. So now, like I was saying, this parallel combination here is to be added to this series resistor because these two, they are in series also, just like what we saw here. We had to combine the two. So after you combine, you now have a single resistor here. You combine that resistor with what? You combine that resistor with a 30 ohm resistor. That is the concept in this case. So it's like in actual sense, it's like we have got something like this here. We've got combined part. All right, we combine this, it's a single resistor. Combined to this one, it's now a single resistor. All right, so that's what I'm trying to say. So meaning to say we are going to calculate the series part of this one, which is the second one, since this was our first. So our series 2 is going to be what we got from this parallel combination, which is our RP1 plus the resistor 6, R6. All right, so that means we are going to have the RS2 in this case. So if we add this, we are going to have 4,992 plus the 6 ohm, which is the 30 ohm, I mean the R6, which is the 30 ohm resistor in this case. So that means our second series combination in this case is going to give us something like 34.92. So that's 34.92 ohms. All right. So we have combined these two. We have a single resistor. All right, which is this one. So this is the equivalent that we obtained from this combination. From these two resistors that we combined, we have the equivalent, which is the 50 ohm resistor, which is our RS1, the first series combination that we had. This is the total that we have. So in actual sense, if you are to analyze back this diagram properly, it is going to be like this. I want you to see, we are going to have these two resistors, then we are not yet done with these two resistors and this and voltage. All right, so I'm just going to shorten this diagram in this way so that you can properly see what's happening here. We had our voltage source here, just gonna shorten it, connected to the resistor, which was our R1, this one. All right, which is R1 and R7. So R1 and R7 are not affected yet. So we are going to have our R1 and our R7 like this. So this is what happened. You combined these resistors here in this parallel combination and the series one. This part, you got this 34.92. So it's now a single resistor, this one. So we are going to have, or to represent this as a single resistor like this. We had a parallel combination. So this is now a single resistor. We combined everything. All right. Then on this other hand, also we combined the two resistors which were in series, these two resistors, these ones. We combined them and we got this 50. It's now a single resistor also, this one. So we're going to indicate it as a single resistor so that we can properly see what's happening. All right, so this is our RS1, this one, which is our 50 ohm resistor. And this is our second one that we calculated, our RS2, which is 34.92 ohms. And having our R1, the original one that we had from the, we never talked about this 15 and this 12. All right, so you're gonna have our 15 here, 15 ohms, and our R7 being 12 ohms. And this is our supply. We are not worried about this. We are talking about resistance, you see. So From this presentation that we see here, how can we calculate the total resistance now? It means we are supposed to combine these two resistors which are in parallel and combine to R1 and R7, making it a series circuit. So meaning to say at the end, we are going to have our formula for RT as R1, this one, all right, plus the combination that you're going to obtain here. You combine these two resistors in parallel. So we are going to have another parallel combination. Let's just call it RP2 since we have got RP1 here. After this, you are going to this R7, which is the to find the total resistance. All right, knowing that RP, it's a parallel, so you're going to apply the product over sum. Remember, in parallel, I said it's product over sum. All right, so that means we are going to have our RT. R1, which is 15, so that will be 15 plus the second parallel combination here of this part product over the sum. So you're going to multiply 34,9 to multiplied to 50. Going to multiply to 50 everything over 34.92 plus 50. All right, so we apply the product over sum concept. After that, this part is branching, okay, going to the 12 ohm resistor also in series. So you're going to add your 12 ohm resistor also there, which is in series. So this gives us the total resistance of our circuit. What we are worried about there is this part here that we are going to have. So this is our RP2, this one. It represents our RP2, this one. All right, so let us just calculate it so that maybe we might need this value later on. So let us just properly see its value. It's going to give us 20,561, something like that, if we simplify this on our calculator. So that means this is our parallel, second parallel part, that one that we combined from the these two resistors. Then adding these two, or adding these three together, now we combine everything, we're going to obtain something like 47.561 ohms. So remember, this is the total resistance, and our resistance is measured in what? In ohms. So that was the question, 8 marks for that. So it means you are supposed to analyze your information properly. Analyze how the currents are taken, how the circuit is given in terms of the resistances. All right, let us check the other part now, which was on 2.2. 2.2, we are now given to calculate the total current. All right, we have the total resistance, so we are simply going to take it from the total voltage that we have in this case. All right, so to remember that the total current, we divide voltage to the resistance. So let me just write it here, 2.2. So our total current, there we have got the total voltage over the total resistance. Remember, our total voltage was 120. So that's 120 over the total resistance. Already we have it here, 47.561. All right, so simplify this. We are going to obtain something like 2.518. So that was 2.5183 and so on. So which is 2.518. So this is your total current measured in amps. So remember, your current is measured in what? In amps. So meaning to say the current flowing across this circuit here is our total current. The one that is going to branch is 2.518 amps. So it is going to fall here, then it branches to current 2 and current 1, then goes back again. So we shall talk about that part, how it branches. Then now they're asking us to calculate the voltage across R7. All right, where do we have R7? This is where we have got our R7. If we check from our diagram here, like I was saying before, that the current that is flowing here is the same as the current at R7, and that here, so it's the same. R7 is affected by the total current. So if R7 is affected by the total current, the voltage across it, we are just going to multiply by the current. So this one is going to be VR7, which is the total current times the resistor 7. And our total current, we have it 2.518 times our R7, which is 12 ohms. So that was the idea of this question, which is going to give us 30,216 volts. All right. So that was it on this one. Direct 2.4, calculate the currents I1 and I2. All right, that is 6 marks for that. What is it that you're supposed to do? There are so many options that we could have taken here to calculate I1 and I2. Let me explain it this way. This is where we have I1 and I2, and we know that here the current that we are going to have here could be calculated from the voltage. Like we just have to know the voltage, the total voltage of this part. All right, we just have to know the total voltage of this part. You divide by the current because it will be the same. So what we are going now to do is we need the total voltage so that we can relate to say in a parallel circuit, the voltages are the same. The voltage across here and the voltage across here are the same. So we need to calculate the total voltage of this parallel combination. This is the first part that you can use. I'm going to explain from the current divider rule. So you have to calculate the total voltage of everything that you are given. All right. So instead of us having this to say we calculate the total voltage from everything that we are given, we just ask ourselves to say, what was the total resistance of this parallel combination? Because we talked about this parallel combination as a whole. What was its equivalent resistance? We go back here on this one, that was our RP2 on the parallel combination as a whole. That is where we have this one and this one combined together. Here we have combined all the resistors that were there, and we remained with this parallel combination, this one. So that is what I'm trying to explain, to say instead of you working with each resistor, you are simply going to work with the combined part, this one. All right, so this reduced on this diagram, we saw that here, this is where we have our current 2, and this is where we have our current 1. And we now have the total current. Remember, we calculated our total current. It was, our total current was being 2,518. All right, remember our value there. So in order for you to calculate this I1, we've got two options, the one of using the current divider rule and the one of subdividing these. All right, so subdividing your voltages, it means you are supposed to calculate the parallel combination voltage. So this is 2.4. All right, we are supposed to calculate the total voltage of this parallel combination here. All right, so it is going to be given as, so we are going to have the parallel, or I don't know, whatever that you're gonna have. So you're gonna have the parallel here, which is going to be the total current. So it is the total current multiplied to the total resistance of this parallel combination, which was our RP2, this one that we calculated here, RP2, this one that I was saying. We are supposed to indicate this, which was 20,561. So that was our RP2 there. So we are going to multiply to RP2. So that is it. Total current being 2,518 times our total of everything of this parallel combination, the one that I was saying, that was 20,561. All right, so if we are to multiply this now, we have got 51,773 volts, which is the voltage that we have across the parallel combination. And we know that across the parallel combination, the voltages are the same. So meaning to say this voltage is the one across this resistor. This same voltage is the one across this resistor. So it means we can be able now to calculate these currents, that is current 1, because this voltage is the same. So current 1 is going to be VP over RS to this resistor. You divide to the resistor that is given. And our VP being 51.773 divided to the RS2, which is this resistor, of 34,92. We are going to obtain current 1 from there. All right, so our current 1 is going to be at the end 1,483 amps, something like that. All right, then we move on to current 2. So our current 2 here is going to be the same voltage, because I said voltage is the same in parallel. So the voltage in parallel divided to the resistance that is affecting our current 2. So that means, all right, let me just save it down here. So our current 2 at the end was going to be VP over the series resistor that we had in this, our RS1. I remember these ones with one that we calculated before. So VP being 51, so that will be 51,773 over 50 ohms. All right, so from there we have got our current 2. That is how we could have calculated this, which was going to give us something like 1.035 amps. All right, but instead of doing this, instead of calculating the voltage for the parallel, then you divide, what else can we apply? We can simply apply the current divider rule concept. So we could have worked this question 2.4 in this way, using the current divider rule. So using the current divider rule in this case, which states that if I am to calculate the current which is flowing across this one, the current I1, I use the opposite the other resistor over the sum of these two resistors times the total current which is flowing. The current that is flowing here, our total current, is the one that branches here and it branches here. So our formula is going to be current 1 is equal to, you use the other resistor which is opposing to current 1 on top. So that's our RS1. So it is going to be RS1 over the sum of these two resistors, which is RS1 plus RS2. So we're going to have RS1 plus RS2 times the total current. So from your current divider rule. So that means here our current 1 is going to be the current on the opposite resistor from the one that you are calculating. You use the resistor that is opposite. You are calculating this current, but you use the opposite resistor on top. All right, so that is going to be 50 over the sum. These ones you just add 50 plus 34,92. Then you multiply to the total current, the one that is branching into these two currents. That is the total current of what? 2,518 amps. So this was giving us the answer direct. All right, so if you multiply here the current 1, it is going to give us something like 1,483 amps. All right, that was our current 1 from this. The same if we are to calculate current 2, this time we are calculating this current 2. So you use the opposite resistor on top, the one that opposes where there is current 2. So use this one on top. So our formula is going to be RS2 now on top, and you add these two resistors. So that's going to be RS1 plus RS2 times our total current. All right, so that means I2 was going to be opposite resistor on top. So that's 34,92 over the sum. You are going to add these two, the sum of these two, 34 plus this times the total current, which is 2.518 amps. So that means we are going to obtain I2 in this case, which was going to be something like 1.035 amps. So it's just the same as this part. So as you can see, this one, when you are using the current divider rule, it's something that is actually exact from what you're given. This is exact. Yes, this part, if you understand, it's fine. The part of calculating the voltage across the parallel circuit, because already also you calculated the total resistance for the parallel combination. So it's just a continuation from that resistance of the parallel combination. You calculate the voltage of that parallel combination, and knowing that in parallel the voltage is the same, so you're simply going to divide voltage divided by resistance to obtain the current. Voltage divided by resistance, you obtain the current. So both ways can be easier to apply as long you understand properly what you are given. All right, then on the last part we are given here to calculate the total power consumed in the circuit. So this circuit is consuming power. So the total power must be from the total resistance, from the total current, from the total voltage, depending with which part you want to use. But we have everything here. So I'm just going to list the formulas, but you can calculate and check if your answers are just in the same direction. Remember that power can be given as I squared R from current and resistance. Power can be given as VI from voltage and what? From voltage and current. Power can be given as V squared over R from voltage and what? Resistance. So here I'm just going to pick one, but you can just use any of these formula because you have everything in this case. So in this case, I'm going to use total current and voltage. I have total current here and I have the voltage from the circuit. So meaning to say, I'm going to use this one. But like I said, you can take any formula from those ones. So our power, I'm going to use total voltage times total current. So meaning to say, our total voltage, remember, it's 120. So that's 120 times the total current, 2,518. So the total voltage, don't forget from your diagram, you're already given here, total voltage of 120. So that means we can multiply these two. By multiplying these two, we are going to have the power there of 302,16 watts. So you're not going to obtain exactly the same answers like 302,16. Maybe it can be 302, but having 302 on your answer because you are using rounded figures. You were rounding off these values, so you're not going to obtain the exact answer from this, but you see that the answers, they'll be in the same range or in the same given values that you have from the first one here. So that was it, 20 marks for that. All you need for the DC circuits is to actually understand all the applications of your resistors, your voltage, the flow of currents. It's not just the given calculations, but the flow of currents on your circuit can also help you to attempt. And also don't be scared of the diagram. By just looking on the diagram, then you see a lot of resistors, then you think it's difficult. Analyze your information properly and check how these are given, how the resistors are combined, or how are they given. All right, so let us check question 3. Complete the table below by giving the appropriate conversion next to what? Next to the correct question. So just have to call, all right, like there's a conversion that was happening degrees to radians. All right, so for conversion of degrees and radians, you choose which one is best. But when given like this, your answers here, as you can see, the other values, they're in terms of pi. So which conversion did they use this one? They use this conversion that pi radians is equal to 180 degrees. So pi in radians is equal to 180 in degrees, which can be taken from 2 pi is equal to 360 degrees if you want. So you can use this conversion or you can use this conversion. All right. So as for me, I'm just going to use this one. Pi is equal to 180. So you just check where are you converting to. Here, we are converting from degrees to radians. So if we are converting from degrees to radians, it means here we are going to have 45 degrees this side, which is equal to our main radians. We do not know. So it's going to be 45 over 180 times pi. So it's 45 over 180 times pi like this. All right, which you can simplify on your calculator. This one, 45 over 180 times pi. On your calculator, it is going to be a 1 over 4 pi. So this one, it is going to be 1 over 4 pi, or simply pi over 4, or 1 over 4 pi. All right, then here we are given pi. already I said pi is 180. Pi is equal to 180. So this one is 180 degrees. If you are using this and they want pi, if you are using this, 2 pi is equal to 360 and you want pi, you simply divide by 2 by 2. So pi is equal to what? 180 degrees. So just a play around of these two conversions. All right. Then we have got 5 pi over 4 to degrees. You are converting from radians to degrees. When you are converting from radians to degrees, it's a simple one because you already know that pi is equal to 180 degrees. So you simply substitute when you are given 5 pi over 4 like this. You simply substitute pi, it's 180 degrees. So we can simply substitute 5 times 180 degrees over 4, like straight like that. Your answer is already in degrees. So that is what you can have. And this one is going to give us 225 there. So this one was going to be 225 degrees. All right, then we've got 300 degrees. For degrees now, we checked this one. And a number in degrees was going to be written like number in degrees over 180 times. So here our number in degrees is 300. So it's going to be 300 over 180 degrees times what? Times pi. That is how you convert from what? From degrees to radians. The number in degrees over 180 times pi. So this was going to give us 5 over 3 on your calculator. Use your calculator direct. That will be 5 over 3 pi. So here we are going to obtain 5 over 3 pi or 5 pi over 3, which is one and the same thing. All right, we are back to again radians to degrees here, where I said from radians, we just have to substitute. You know that pi, it's 180, just like this previous part. So it's going to be 11 pi over 4 was going to be 11 times pi, which is our pi, it's 180 in degrees. All right, over 4, just like that. This is going to give us 330 degrees. All right, so there we are going to obtain 330 degrees. So that was just the conversion part. You just need to know how to convert from one to another. Play around with your that was 10 marks. Okay, just for that, guys, 10 marks. Okay. 3.2, refer to the AC circuit below in figure 2 and answer the questions, the following questions. All right, so there we've got an AC circuit. Let's try to analyze our AC circuit and see what's happening here. We've got resistance and capacitance only. Okay, so this one can be easier. We just have two things. Then we are given the total current, the voltage across the, we've got the voltage across the resistor, the voltage across the capacitor is not given. And we have got the total voltage and we have got the frequency. Okay, this is what we have. Let's see. Calculate 3.21. Calculate the impedance Z of the circuit. Where can we obtain the impedance? All right, we've got total current, we've got total voltage, so you can have the impedance there. So 3.21, the total impedance is simply going to be the total voltage over the total current because we have this, okay? 220 over the total current of 20 there, meaning to say we are going to obtain our impedance of 11. So this will be 11 from your calculator. That will be 11 ohms. Impedance is just like resistance. So even the units are the same. It's not just different to say impedance is for AC, but the units are the same. 3.22, calculate the voltage across the capacitor VC. All right, so we need the voltage across the capacitor here. Remember that I talked about this, guys, whenever you're dealing with the AC, the voltage, this one, the total voltage that you see here, that the one that you are given, is not just to add to say VR plus VC, no. This one is a phasor sum of the given voltage, which is given by the formula. Let us write it here. All right, so this will be 3.22. The total voltage is a phasor sum of the given voltage, which is the square root of VR squared plus VC squared, depending with what if you are given an inductor, it will be VL squared. So from this formula, we can manipulate to calculate VC. We have VT in this case, which is the total voltage here of 220. So that's 220 is equal to the square root of VR squared, and VR we have on our diagram, which is 150. So that's 150 squared plus VC squared, which is the one that we are supposed to calculate in this case. So we are going to have VC squared. How do you remove the square root? You are going to square both sides. So here we are going to square both sides, meaning to say we are going to remain with 220 squared in this case on this side. So 220 squared is equal to, we have removed the square root, so we are going to remain with 150 squared plus VC squared. All right, so I want VC squared. I'm going to transfer 150 this side so that it can be a negative there. So it's going to be 220 squared minus 150 squared, which is equal to VC squared. So this one can combine on your calculator, guys, to find your VC squared. So meaning to say our VC squared is going to be what? Just combine this part on your calculator, 220 squared minus 150 squared, which is in this case is going to give us 259,259,00 like that. So to remove the square, remember we introduced the square root. We introduced the square to remove a square root. Now we want to remove the square. What are we going to introduce? We are going to introduce the square root, the opposite of what we did previously. So that means our VC now is going to be something like, we are going to obtain something like 160,935. So it is taken from the phasor sum of the voltage here. VT is the phasor sum, not just to add the two. You have to apply the phasor sum formula, which is VR squared plus plus VC squared for VT. Then manipulate your formula to find VC. That was it. Okay, that was it there. All right, let's check the other part now. They want us to calculate the capacitive reactance XC. All right, we now have this voltage here. We now have this voltage here, which is 160,935 volts in this case. And now we want the capacitive reactance XC. So we can calculate the reactance because here it's a series circuit where current is the same. So current times XC should give us VC. So meaning to say VC is simply, XC is going to be simply taken from the voltage. Okay, let me just use this space here. All right, here, let me use this one. So meaning to say, we are going to have, this is 3.23. So we are going to have this as XC is equal to the voltage across, because we are saying current is the same in a series circuit. So it is going to be the voltage across the capacitor over the total current, which is the same. So that means our XC will be the VC, the one that we calculated, that was 160,935 over IT, our total current of 20. All right, so we have got our XC there, which is going to be equal to 8,047 ohms. All right, so that is a reactance, so it's measured in ohms. So here this IT is equal to IC. Our formula was supposed to be VC over IC, but this IC and IT was, it's a what? It's a series circuit where we know that in a series, current is the same. So that was the idea of this question here. Then after finding XC, now they want us on 3.24 to calculate the value of the capacitor C. All right, so where are we going to have the capacitor now? We are going back frequency. Remember, our frequency here is 50 hertz. So taking this frequency and our XC here, we can be able to calculate this. Remember, our frequency is 50 hertz. So we are going to formulate a formula now. So 3.24, remember, XC is taken from 1 over 2 pi FC, which is the same. If we make this C the subject, you are going to see that the capacitance is equal to 1 over 2 pi FXC. So these two, they're just taken from the same. So we have we've got everything on this formula actually. So it's just a matter of substituting 2 pi times the frequency of 50 times our XC, which is 8,047. All right, so that's it. You're gonna use your calculator in this case. So if you are to use your calculator direct like this, you are going to obtain something like 3.955. Okay, let me explain it on a calculator so that this part we do not confuse with this part here. If you are to check here, this is what you're going to have on your calculator, 1/2 pi like this times 50 times 8.047 like this. This is what you're going to obtain. This number that you are obtaining here is raised times 10 to the power of -4. So this is what I'm trying to explain, to say you're going to have your answer like here, it was going to be 6 something, but measured, written like 10 to the power of this was 3, is 10 to the exponent of -4. All right, but it's not gonna make sense for us to leave our answer like this. Try by all means to have your answers in terms of you can change to microfarad, nanofarad, and so on, knowing that the from -4, the number that we can target is the microfarad. Micro means times 10 to the exponent of -6. That a microfarad, it's a number that is times 10 to the exponent of -. So to convert to microfarads now, you do the opposite. You multiply your answer by the opposite of the inverse of this, which is going to be a positive. So this answer that you see, you multiply by 10 to the exponent of 6, meaning to say automatically your answer is going to be now in the microfarads. The moment you do this, your answer is going to be in microfarads. So what am I trying to say here on this answer? You are going to multiply by 10 to the exponent of 6 like this. Your answer automatically is now in microfarads, which is going to be 395,563. All right, so you're going to have 395,563 in microfarads. All right, so that is going to be our capacitance. So this is the idea that you simply work with depending with which part exactly do you want to convert your answer to. But it is best to leave your answer in microfarads for capacitance. All right, 3.25. Now we are given to calculate the value of the resistor R. All right, we need the value of the resistor R here. This one, guys, is direct. We've got voltage across the resistor, current across the, suppose this is the total current. So in actual sense, our formula was supposed to be the resistance is the voltage across the resistor over the current across the resistor, but the current across the resistor is our total current. So we are simply going to use the total current there. So our resistance is going to be the total voltage across the resistor, 150 volts. So that will be 150 there over the total current, which is the also across the resistor, because the current there is the same. So you divide by 20. So that was our total resistance, which is 7,5. All right, so that was it. 7,5 ohms. Remember, we are talking of resistance, and resistance being measured in what? Being measured in ohms. So that was our question 3. Question 3, everything, 20 marks for that again. So let us check the other part of our question, which is now question 4. Draw a neat and clearly labeled IEC circuit symbols for each of the following components. So this time I'm just gonna draw, guys. I don't have option. All right, so we've got the light emitting diode, which is our LED in this case. All right, so it's diode that is facing out, remember. Yeah, but you guys are supposed to draw something neat. Here I'm just giving you just like a sketch, guys. All right, so we must have a diode like this, but it's emitting light. So if it is emitting light, it means the light is going to be out like this. It's going out. That's emitting light. All right, so that's a light emitting diode. All right, then we have got a varactor. In this case here, the varactor diode is just that is the diode that you simply have. But this one, let me just write closer because you'll be now confusing to say which one is this. It's just a diode that you have, but it has like a capacitor thing. There's a capacitor thing like this. That's a varactor diode. All right, just a normal diode, but having that capacitor thing, or you can have it a normal diode like this. Then you indicate inside here with a symbol of a capacitor inside. You must indicate a symbol of a capacitor there. All right, so that was it. Then 4.13, we have got the photodiode in this case. The photodiode, it's simply from all right, same as the previous part, a light emitting diode, but this one, it is going to be taking in light. It's a photo that it will be taking in light. Now that is the difference between that one. Or you just indicate a diode, then you indicate something like this. All right, if you don't put this, then that will be something like that. All right, so the other part there, it's a Zener diode. These ones, guys, all right, Zener diode just from our normal diode, but this time we shall have something of this nature. That's a Zener diode. Indicate a Zener diode now. All right, we have our anode and our cathode on this side, or we can just represent only this one on top, then this one straight like this. Still one and the same thing. All right, then we've got the PN junction diode. This is a normal diode, the normal one that we are used to, our normal diode, guys. This is the one where we have got our anode and our cathode in this case. All right, so that was it. Name 2 types of rectifier circuits. On this one, we are asked to name 2 types of rectifier circuits. So remember, on our rectifier circuits, we've got a half wave. So we have got a half wave, which is the one that uses one diode. So that's a one diode circuit. That's a one diode circuit in this case. Then we have got a full wave. All right, we have got a full wave in this case. So a full wave, it can be a 2 or a 4. It can be a 2 or 4 diode circuit. 4 diode circuit. So that is when you are talking about a full wave, it can have 2 diodes, okay, or it can have 4 diodes on a bridge. All right, so that was the part of the question. Then 4.3, we are now given that a Zener diode can be operated in both reverse and forward bias mode. Mention 3 properties of Zener diode. Whether it's operating in the question here is to list to mention what are the properties of Zener diodes. That is what the question is all about. This statement does not even help us at all. All right, so in this case, I've got some of these ones for me to write. They are gonna be much. So let me just show you here. So these are some of the properties that we're gonna consider on our Zener diode. All right, when it is used in the reverse bias mode, it has the ability in this case to maintain constant voltage across its terminals and current to flow in the reverse direction, that is cathode to anode. So that is, we are saying it has the ability to do this. It has the ability to maintain the constant voltage. All right. Talking of the same Zener diode, when is used in a forward bias mode, it acts as a normal. Whenever it is in the forward bias, it acts as a normal PN junction diode and allows current now to flow from what? In the forward direction, that is anode to cathode. Now it's a normal diode when it is like that. All right. Then when reverse biased, the Zener diode does not allow current to flow initially until its Zener breakdown point is reached. So until you've got a Zener breakdown, at this point, the voltage across the Zener diode remains constant. So these are some of the properties that you needed in this case to answer this question. All right, 6 marks for that. Then on question 5, we are now given there to mention 4 advantages when using transistor as a switch. All right, so there we can talk of, all right, this one I should have just listed these ones. I should have just, okay, anyways, let's see. So you need 4 advantages when using transistor as a switch, All right, so we can have this, these are disadvantages. So we've got a small base current there, a small base current, a small base that is emitter current, all right, a small base emitter current. All right. Can switch on, off, all right, can switch. Let's just hope it's gonna be fast. Can switch the transistor on or off. All right, so that is the first one. Then also you can consider there is no way NT in this case. How many do we want here? All right, main 4. All right, so let us have another one. So we can consider this also our transistor. There is no way NT. All right, when you are talking about, it's not like we are dealing with those machines that they are gears, this and that. Here, there's no way NT. All right, there is nowhere NT. All right, so that is on switch gear. Okay, this is on switch gear caused by etching. All right, so that is another part that you need here. Then it's much faster. All right, we've got much faster switching times, much faster switching times. And also we have to consider the control over long distances. All right, so the control over long distances. Over long distances in this case. All right, so there are so many. I just have to be careful. All right, so I just I'm supposed to just prepare this on this document just at once. But anyways, let's just hope we are together. Then on 4.2, we are now asked to draw a neat labeled circuit diagram of a common base. Take note, it's a common base transistor amplifier making use of what? NPN. All right, so it is using an NPN and being a common base. All right, so that's 5.2. Let us just have it here. So I'm just gonna have a sketch here of what you're supposed to have, but you're supposed to draw neat and accurate. All right, so this is what you're gonna have our input capacitor here to the transistor here. It must be NPN in this case, so this one must be an NPN. All right, so we're gonna have something like this, NPN. So this is our NPN transistor. That's the first thing not to forget, because remember that NPN is going out, PNP it be coming inside like this. All right, so here we go to the voltage divider. This is our voltage divider here, where we've got our R1 and our R2. Just to sketch this one. All right, so you're gonna have your R1 here, your R2 in this case. All right, then this one to the output, which is the VCC in this case. All right, then here again we are going to the output. All right, something like this, passing through RC from our VCC of the collector. Then we've got the output in this case of the capacitor. And in this case, we've got our plus VCC. All right, so that's the sketch there. That's the sketch. I think we are together there. This one connected to the base, and here we've got our input, V in, and the input of the capacitor. Then definitely here we're gonna need V out. All right, also it's an AC, this one. Okay, so yeah, I think just hope I have everything. So the NPN transistor, so that is how we could have our common base. All right, so the part there is the common base. That's why we have to get our base to the what? To the ground. All right, and the use of the NPN transistor. All right, so that was the major part. State the operating principle of the light dependent resistor that is now on 5.3, and also draw the following. the circuit of the LDR and the characteristic curve of the LDR. All right, so you just need, like, we are explaining the properties of LDR, in this case, the light dependent resistor. All right, so let us check the principle. That is the first thing. Right, so the LDR in this case, definitely it is operating with a light. All right, so under this LDR, we are saying when the incident light, in this case, incident light falls across or falls on it, all right, falls on the device, its characteristics, which is the resistance, in this case, it's a resistance decreases. So we are going to have a decrease in the resistance, causing a current to flow through the device. All right, so its resistance is going to decrease, and its resistance decreases, causing, so this one is going to cause a current flow, causing a current to flow through the device. All right, so that is what you simply have in this case. That was our question. We just need the principle of operation. What is happening when the light is applied to the device, which is our LDR? Then its resistance will decrease, causing a current to flow through the what? Through the LDR. Then the other question on 5.31 now was to give the circuit symbol. 5.32, the characteristic curve. All right, so we need the circuit symbol of this LDR, which was 5.31. This is 5.3. So it's now 5.31. So the circuit symbol, or this one, it's a light dependent, it's a resistor, this one, which is depending on what? On light. So it's a resistor that is depending on light, like this. All right, so that means it takes in the light. The light is going to be falling into our LDR in this case, whatever, but the light is supposed to be going into the LDR. That is the concept. All right, then on 5.32, they wanted the characteristic curve now. So I want us to take the characteristic curve, because here we are talking about light and resistance. So meaning to say, we are going to be comparing what is going to happen due to the light intensity and the resistance. So this is our light intensity on this side. And on this side, we've got our resistance, this side. So here we've got our resistance in ohms. So what is going to happen? We said when the light falls on the device, the resistance decreases. The resistance decreases. This is our resistance in this case. So meaning to say, on this side, the more light that we are going to be having, as the light is increasing, the resistance is decreasing. Meaning to say, as the light increases, the resistance is going to be high. So here we are going to have our diagram like this, our curve like this. The resistance decreasing as the light is increasing, like this. As the light is increasing, the resistance is decreasing. That is the major part of our explanation that we had before, if you still remember. All right, so that was question 5. Then question 6, give 5 advantages that a digital multimeter offers over analog multimeters. All right, so they will be talking of the issue of accuracy, that the accuracy is higher there. So we are going to be talking the issue of accuracy, that accuracy is higher. Then we are going to be talking about the strength being more robust, that is being stronger than, and much more sensitive. These ones, they are much more sensitive. All right, so in terms of sensitivity, then also the error of parallax is limited. All right, so we will talk of the error of parallax being limited. In this case is limited, can handle negative quantities, also can handle negative quantities can handle negative quantities, that is working with negative values, then there is no guessing. The guessing is actually limited. We get the exact values that we are given. It's not to say you can't see the value. The value is properly displayed, so you do not guess the value. You see the proper value. So that is the guessing is eliminated. You know the exact value. Don't guess to say maybe is this or that. No, you need exact. So that is the advantages that digital meters have. All right, so now we are given, in this case, a moving coil. All right, so let us just have our information here. So we've got a moving coil that we are given here that has got a full-scale deflection of 1 milliamp. Remember, I always said, guys, when you are given the full-scale deflection, that is the current, these are the measurements which are taken from the meter that you are given. Like this is our meter here. So this is the current across the meter of 1 milliamp, and an internal resistance of 27 ohms, which is the resistance of this same meter that we have of 27 ohms. So the question is to calculate the value of the shunt resistor that would enable the meter to be told the shunt resistor, and the shunt is connected in parallel. From the meter here, we are going to have our shunt resistor connected in parallel. So we want the current that is going to enable this meter to measure a current of 10 milliamps. So meaning to say there's a 10 milliamps now entering our circuit instead of 1 milliamp. For it to be able to measure 10 milliamps, what is going to be the shunt resistor needed? So we are going to have our shunt resistor in parallel. Remember, the shunt resistor is in parallel. That is like this. Now it is to measure a certain value of 10 milliamps instead of the 1 milliamp that it is used to measure. So remember that in parallel the voltages are the same. So here we are going to have 1 milliamp is the only current that is going to flow across here. So meaning to say, out of the 10 milliamps that we have, the rest of this current is going to flow on this side. So it is going to be 10 minus 1, which is 9. So we are going to have 9 milliamps flowing across the shunt resistor. This one cannot carry more than 1 amp. The rest of the current will be adjusted to the shunt resistor, then it goes to the other circuit. It will not even pass through this meter. It will pass through the shunt resistor. So which value is needed? What value do we need in this case to in order for us to have this resistor? I mean, in order for us to measure this 10, that is the percent. So how are we going to calculate the shunt resistor? Like I said, in parallel, voltage are the same. We are done with this 10. Now we are focusing on this diagram now to say in parallel, the voltages are the same. So meaning to say, we are going to have the current here of the shunt resistor times the resistor of the shunt, that's voltage times current, should be equal to, here we have got the current across the meter times the resistance across the meter. So we can calculate the shunt resistance here if we divide by this shunt current both sides. If we divide by the shunt current both sides, that means we remain with the shunt resistance. All right, so that means our shunt resistor is going to be given from the formula IM Rm, current on the meter times resistance of the meter over the current of the shunt resistor, which is the current of the shunt is this one that we calculated, the 9 amp. So it's simply taken from where? From the total current, this one, to say the total current plus the shunt current is the one that we are. So the total current is equal to this one. It will be equal to the sum of these two. All right, then you make this one the subject. So that was our shunt current, this one. So that means we can simply substitute here current across the meter, 1 milliamp. So that's 1 times 10 to the exponent of minus 3 times Rm, which is 27 over R shunt, the shunt over I shunt in this case, which is 9 milliamps. So that's 9 times 10 to the exponent of -3. All right, so this gives us the resistor across the shunt from your calculator. That was going to give you 3 ohms in this case. All right, but this one you could have seen that this is the same. This is the same. So you're simply dividing this to 27 divided by what? By 9. So that is going to give us a 3 ohm. Or just use your calculator, guys. Use the calculator, still one and the same thing. All right, so that was our question here on question 6, the first part of our question 6. Then we still have another part here whereby now we are given define Lenz's law. All right, the Lenz's law. How do you define the Lenz's law? That is the consideration of our question. All right, so here I've got something here. Last time it was a lot. All right, that the EMF induced in a circuit, in an electric circuit, always acts in such a direction that the current it drives around the circuit opposes the change in the magnetic flux. That is the Lenz's law in this case that we are given. So then the other part on 6.4 was to draw a circuit symbol of a synchro receiver, meaning to say there are so many ways that you can put these synchro receivers, guys. All right, but here I'm just going to indicate this one in an easier way. All right, that should be this way. So we are going to have R1 on this side, R1 and R2 on this side. So I've got R1 and R2. Then on the other hand, here we shall have S1, S2, S3. That's the easiest one that I think maybe you can need. But there are so many symbols. If you check, there's another video that I had on this one where we work with so many symbols that you can actually use or that you can actually have. But in short, I think this one is the easiest one that you can even analyze and see. So that was what you're supposed to have, guys, in this question paper, having a total of 100 marks. So all you just need is to make sure you revise your areas so that you see, are you preparing for the next stage, or you are preparing to rewrite this part if it is that a condition. But whatever condition it is, this is the right time to work on everything. If you are to advance, start now to work on those areas. If you are to rewrite this, start now to work on the basics of everything so that you'll be able to prepare again for the exams which are ahead of time. But for now, guys, that's it from Mason African Motives. Till we meet again.